And welcome to another video then, and this one is the first in a series on logic, specifically as it applies to electronics. Now there are two sorts of logic, combinational, which is what we're going to be looking at in this video, and sequential, and the difference between them is that combinational relies only on the state of its inputs currently, whereas sequential has a memory or some sort of feedback. So we're going to be looking at logic gates in this video, but to do that we need to define some terms before we start. And we'll start with defining low, high, 0, 1 and so on. And what we're going to start with then is this chap, George Boole, who lived between 1815 and 1864. And like Newton, he came from Lincolnshire. And there must be something about living amidst all the potato fields that is conducive to great thought, because what Boole did was he looked for a system that would take mathematical logicalities and put them all together and come out into a logical outcome given the incomes. And this flowchart here represents what he thought. So, ignoring this one for a moment, and we'll call these A, B, C, and the outcome Q. What happens if A and B and C are true is that you will get a logical outcome Q which works as a predefined process and can be repeatable and tested and tried and true every time. However, if we've got four inputs, A, B, C, D, and A and B and C are true, but D is not, that will affect our predictable outcome. And he came up with an equation, A, B, C, D equals Q. So, A is true, B is true, C is true, D is not true. Naturally, Q will not be true. However, there may be occasions in which something that is not true will lead to a predictable outcome. So all these three are true, and all that is true, that is not true, sorry, and what we'll get is the predictable outcome from that not being true as well. And he covered that. A, B, C, and bar D, i.e. the opposite of D, equals Q. So A, B, and C are true, D is not true, Q is true. Now sometimes you may have a situation whereby any situation given is true, and that will produce a true outcome, regardless of which of these three inputs, or indeed two of them, or all three of them, are true. The predictable outcome will be true too. And here we have A plus B plus C equals Q, giving a predictable outcome. It might well be that if the given situations are not true, then you'll have a predictable outcome for that as well. And here, A and B and C are not true, and that gives us the predictable outcome Q. And Boole covered that. He went A plus B plus C equals bar Q, or the opposite of Q. Now in electronics we can use Boolean algebra to make logic circuits. Boole, of course, dying in 1864, had no interest in electronics. It wasn't a subject when he was around. What he was interested in was finding mathematical probabilities for given occurrences that would lead to the predictable outcome, and he thought in terms of false and true. In electronics, when we make logic circuits, we tend to make them with transistors, and transistors will either conduct or not conduct, and that will give us an electronic signal or a pulse. Now, if there is no pulse present, we tend to think of that as a 0, or we might equally say low. If there is a pulse present, we tend to say it's 1, or we might equally say high. Now these three terms are interchangeable. So where you hear false, you might also hear low, and you might also hear 0. And where you hear true, you might also hear high, or you might hear 1. Around 0 and 1 tends to be what electronic engineers say, although they do say low and high as well. And low and high tends to be what computer programmers say, although they do say 0 and 1 as well. Don't be confused by the terminology. False equals low equals 0. True equals high equals 1. So if you remember that, any interchangeable terms, and I assure you I will be interchanging the terms in the course of this film, will be clear to you. Now in this film we're going to be looking at a lot of logic gates, and really to define our terms further, what we need to do is we need to look at the standards for drawing logic gates, and later on we're going to make some practical ones, but first we need to look on the simulator and see what they actually do. Logic gates can be a very confusing topic, and it's not helped by the fact that there are a lot of competing standards in the drawing of them. I've seen standards by GEC, Alan Bradley, there are German standards, and quite a lot more besides, but the two most common ones we'll see are the ones that we've got in front of us here. And down the right hand column here is the IEEE Standard 91 1984. They're little rectangular boxes. So we've got and, or, not, and, nor, exclusive or. And while we do see those quite commonly, by far the most common ones are these over here. The American standards. Now, most of the computer-aided design programs and most of the simulators will use these. So, throughout this topic, I'm going to be referring to these standards rather than these, as we will be doing a lot of simulation, and these are the standards used in the simulator. And so we'll begin then by looking at some gates in the simulator, and there are really only 3 kinds of real gate, although you can put them together to make lots of different others. So what we've got here is we've got the NOT gate, which is the most basic. It's also known as the inverter, and we'll see why. If we start the simulator running, we'll see that we've got a 5-volt logic input, that's high, but the logic output is low. If we turn the logic input to low, the output goes high. And there's the truth table. When A is 0, Q is 1, A being the input and Q being the output. When A is 1, Q is equal to 0. And underneath we have the Boolean expression for it. Q equals bar A. Bar A, of course, is the opposite of A. Next we come to the AND gate, and the AND gate, as it suggests, will only go high when both the inputs A and B are high. Well, let's test it and see. We've got the simulator running, so A equals 0, B equals 0, A equals 0, B equals 0, Q should equal 0 as well. If we set A to 1 and leave B at 0, Q equals 0, so that's true. If we set A to 0 and B to 1, Q should equal 0, and that's true. And if we set both A and B to 1, Q equals 1. And there's the Boolean expression underneath, Q equals AB, A times B. So 0 times 0 is 0, 1 times 0 is 0, 0 times 1 is 0, but 1 times 1 is 1, and there's the output. Now, I mentioned a while ago that there are only 3 kinds of gate in reality, and this is the example of the first one. This is a NAND gate, a not AND gate, and basically what it is it's an AND gate, as we saw before, with a NOT gate stuck at the output, and this little bubble here is the inverter bubble and tells you that that is a NOT output. So it does exactly the opposite of the AND gate. If we remember the truth table for the AND gate, and I'll just roll over a bit so we can actually see it. There's the truth table for the AND gate, and you'll see that it's exactly the inverse. Well, let's test it and see, shall we? So when we've got 1 and 1 for A and B, Q should be 0. And here we have got 1 and 1. If we set them to any other pattern, what we'll find is that the output is always high. It's only low when both inputs are set to 1. Boolean expression is Q equals bar AB. So we multiply A by B and then we take the opposite. Now similarly, our third real gate is the OR gate. And we can see the truth table for it here. A's equal to 0, B's equal to 0, then Q's equal to 0. But if any input is equal to 1, then the output will be equal to 1 as well. So let's try it. There we are. There we are. And if both inputs are equal to 1, the output is high. The Boolean expression is Q equals A plus B, and we can see how that works. 0 plus 0 equals 0, 1 plus 0 equals 1, 0 plus 1 equals 1, 1 plus 1 actually equals 2, but for this purpose we'll call it equal to 1 anyway, because that's what the output is. And as you probably remember, sticking a NOT gate on the end of an AND gate gave us the exact opposite behaviour of an AND gate, and we've done the same here. Sticking a NOT gate, which is marked by this little bubble, on the end of an OR gate gives us an OR gate. Just scroll over a little bit so we can see the two truth tables. There's a truth table for an OR gate, there's a truth table for a NOR gate, and you can see it's the exact opposite. So the NOR gate should only go high at the output when both inputs are low. Well, we've got both inputs high here, so let's see what happens when we put one low. State remains unchanged. Let's see what happens when we put the other low. State remains unchanged, and when we put both high, state remains unchanged. So if we put both low, and there we are, the Boolean expression is Q equals bar A plus B, which is the opposite of A plus B. So let's check it out from the truth table and see. 0 plus 0 equals 0, and the opposite of 0 is 1. 1 plus 0 equals 1, and the opposite of 1 is 0. 0 plus 1 equals 1, and the opposite of 1 is 0. 1 plus 1 actually equals 2, but remember, for the purposes of this exercise we're calling it 1 anyway, and the opposite of that would be 0. And there we are, so we know the NOR gate works too. To begin with then, we'll go with some very old school technology, and what we've got here is we've got an AND gate and it's constructed out of diodes. So, if I zoom in a little bit here so that we can see what we've got. We've got three just plain, normal, bog standard barrier diodes. They're nothing special, they're 1N 4001s. And what we've got is we've got them hooked in to these switches. And these switches have two positions. And in the normally open position like this, they conduct a voltage to ground. And if you press them down like this, they'll actually conduct the other way. They'll conduct a normal voltage, which in this case is 5 volts, up to one or the other of the diodes. Each switch is connected to one diode. So that one to that one by the looks of things, and that one to that one, and that one to that one. For an indicator of what the gate is doing, we've got an LED, and what I'm going to do is I'm going to press each button individually. And you'll see that nothing at all happens. So I'm going to press 2 buttons at a time. Pressing those 2, nothing happens. Pressing those 2, nothing happens. And pressing those 2, nothing happens. Let's press all 3. I'll zoom out again because I'm not quite sure you could see the LED there. That's better. So, if all 3 inputs go high, then the LED comes on. So how does it work? Well, let's zoom back in on the diodes again. Well, what we've got here is a resistor. Zoom out a little bit. What we've got here is a resistor, and that resistor is stopping current from the LED from being too great, but at the same time it's feeding the anodes of these 3 diodes through these 2 red wires here. And that means that there is a 5 volt potential on the anodes. When the switches are in the normally closed position, they're conducting to ground, so that means that there is a 0 volt potential on the cathodes. As I press the switch, what happens is a 5 volt potential appears there and a 5 volt potential appears there. Now that can't conduct to ground anymore, in fact it can't conduct anywhere, but these 2 still can. And if I press these 2 switches, that one and that one cannot conduct to ground anymore, but this one still can. However, if I press the 3rd switch, none of the diodes can conduct to ground anymore. A voltage is developed that goes across the LED instead. And there it is. Now these are very simple and very basic, and they're easy to make, and people do get a bit sniffy about this sort of technology these days, and it is pretty much obsolete, and it is difficult to cascade anything off them. But what people don't generally realise is that in the very first American nuclear missiles, the Minuteman, this sort of technology was actually used in some of the guidance systems. One of the big problems with this is that you can't construct a NOT gate. You really can't. And if you want a NOT gate out of it, all you've got to do is stick a transistor in there. Now this sort of thing is called diode logic, or because we've got resistors in, diode resistor logic. And if we stuck a transistor in there, we'd be getting into diode transistor logic. Diode transistor logic is not usually worth it in the long run, as there is a thing called transistor logic, and that's what we'll be looking at with our next example. And here's the next example, and it's another AND gate, and if I press one button, nothing happens. If I press the other button, nothing happens. But if I press both buttons together, we've got the LED lights. That's a 2-input AND gate, so let's see how it's working. If we zoom the camera in and pan it about a bit. And here we have 2 transistors, and they're 2 NPN transistors, 2 2N3904s, and we have resistors to bias the bases. And what's happening is, as we push the switches down, we're getting voltage across there and a current at the base of each transistor. They can conduct the positive voltage through here, and through there, and through there, and through there, and into the LED. And it's very simple. And that's really all we need to make an AND gate with. And in front of us here we can see how the transistorized version of the AND gate works. It's very, very simple indeed. We have two incoming levels, and they can either be on 0 or they can either be on 1 in both cases. And that of course would be 0 low and 1 high. And what they do is they go through the base of the transistor. And the transistor is attached to a 5-volt supply up here. The second transistor is attached to the emitter of the first, and when both are conducting we find a path. And we can take from that path whatever we want to. We don't really need a ground path there. We could take it to another sensor or another gate or anything we like, really. So let's have a look what happens when we flip the switches. And of course nothing happens there. You'll see that in the oscilloscope, I don't know if you can see the oscilloscope, but the scale there is 2.63 nanovolts. But if I flip the second switch to make 2 high levels, and there we are, and at this point here we now have 2.82 volts. Well, this is of course an AND gate, and if we move things around, we get rid of that line and that resistor and that line, and we move the output up to here, and the ground connection to the emitter of the second transistor, and we run it again, if we put the multimeter there, you'll see we get a full 5 volts there, and both of them are at logic level 0. If I do this, we've still got the 5 volts, and if I do this, it now goes down to 101.0 millivolts. And that's because the great majority is now conducting through the transistors straight to the ground. And what we've done there is created a NAND gate. Any pattern other than 1, 1 will cause the output to be high. And if you remember the truth table for a NAND gate, that's exactly what it was. Well, these days it's very unusual to find that logic gates are made of discrete components like we've just seen, the diode and the transistor, and what we'll find is that they're all in an integrated circuit packaged together. And what I'm going to do is we're going to go back to the simulator for a while, and we're going to have a look at the NAND gate. Now the NAND gate is very important because both the NAND and the NOR are considered universal gates. And with a universal gate you can make any other kind of gate you want. I have some quad NANDs, so we're going to use the NANDs, and we'll see on the simulator exactly what the NAND is and does. So what we need to do now then is have a quick simulated look at the NAND gate and see what we can and can't do with it. And as we know, the NAND gate will only go low when both inputs are high. Either input's low or both, it'll stay high, and when both inputs are high, it goes low. However, there's something a little clever we can do using multiple gates. And what we've got here is an AND gate made from an AND gate. And it works in the inverse. Only goes high when both inputs are high. The way we do it is we take another NAND gate and we take the output from the first and make the inputs on the second both exactly the same as the output of the first. And by doing that, we invert what we've inverted. And here's a Boolean equation for it. Q equals bar AB times bar AB. At this point we need to introduce a chap called Augustus de Morgan into the proceedings, and Augustus de Morgan formulated a series of laws, and one of them says that if you're inverting an inverse, what you're actually doing is the inverse of the inverse. And if you're taking the inverse of the inverse, it's exactly the same as the original. So we end up with Q equals AB. And of course, for an AND gate, Q equals AB, 1, 1 equals 1. And carrying on then, what we've got here is something a bit esoteric, and it's called an interrupter. And what we've got is two pull-up resistors, each connected to a different 5-volt supply, and that 5-volt supply will be coming out from a subsystem somewhere into this thing, and they're ensuring that the two inputs of the AND gate are kept continually high, except when a switch is flipped, in which case it goes low, and that will send a signal to another part of a subsystem. And this is used in things like safety mechanisms for great machines, or security alarms. If something's missing or something's been tripped, then it sends a signal to sound the alarm. Moving on a little bit, we now have a proper OR gate with logic levels, and if either logic level goes high or both logic levels go high, then so does the output. If both are low, then the output is low. And we've done the same trick as before. We've coupled together in both NAND gates both inputs so that they're both at exactly the same level at the same time. And of course we've done the outputs. Now both of these are low, both of those are high, and that means that the output here will be low. However, if one of them goes high, the output will go low, and as we know, wherever we've got a low input on a NAND gate, we'll get a high output. Now the Boolean equation can be expressed, if you want to, as Q equals bar A, bar B. However, Mr. De Morgan came along and looked at that and worked out that that can actually be transposed to A plus B. And that, as we've seen, is the Boolean equation for an OR gate. So there we are. By using 3 NAND gates, we can make an OR. There is a minute or two more theory before we go into the breadboard to explain what's going on, and this is particularly important when we're using CMOS chips, as we're about to do. So, we have here an AND gate with a couple of pull-down resistors, and what they're doing is they're keeping these pins reliably low. So they're taking any floating voltages off these pins and shunting them off to ground. And the reason we do that is because in CMOS types, what you can get is you can get a floating voltage. There's a cut-off voltage of about 0.8 volts, and under that it will definitely be low. There's also a voltage of about 2 volts, and over that it will definitely be high. But between 0.8 and 2 volts there is a kind of no man's land. It's called the indeterminate zone, in which the chip will not know whether to read a low or a high, and we'll get a false reading at the input. And of course, if we get a false reading at the input, we'll get a false reading at the output too. So, pulling determinant low to ground like that means that the inputs are asserted low, until of course we assert them high like that. Now if you look far enough, there's maths behind everything, and there's certainly some maths behind this, and you can see the equation here. R max, i.e. these, is equal to voltage threshold low maximum over current threshold low. That's quite complicated, and quite often you won't know what the current is. And what most designers do, depending on how conservative they want them to be, is they'll slip in a resistor between 10 and 100k, and that's my usual shortcut. Put in a 10k resistor in there, it works in most cases. Well, just as diode logic gave way to transistor to transistor logic, transistor to transistor logic is now giving way to a technology called CMOS. And CMOS is complementary metal oxide semiconductor, and basically what you get is a load of field effect transistors packaged together to make the logic gates, and they're all done in this little black chip here, and that is a quad NAND gate. It's a 74HCOON. Now, it's common to use NAND gates and NOR gates rather than any others, because both NAND and NOR are universal gates. If you've got a NAND gate or a NOR gate, you can make any other kind of gate from that gate, which you can't do with ANDs, and you certainly can't do with ORs. So, what I've done here is I've taken this NAND gate, or at least two of the NAND gates in this package, and I've made another AND gate. So, if I press one button, nothing will happen. If I press two buttons, nothing will happen, but if I press them both at the same time, as you'll see, that LED will light. Well, let's have a quick look at what's going on here. Now, you'll remember me going on about pull-down resistors, and here I put two pull-down resistors in to make sure the first NAND gate is reliably low when I want it to be. And as we know, when a NAND gate is low in any input, the output will be high. The output of a NAND gate will only be low when both inputs are high. If I press these buttons, both these inputs will be high, and the first NAND gate there will put out a low output. But if it's putting out a low output, how does the LED shine? Well, the clever thing you can do with these quad packages is that you can link them together. And if you link the output of the first AND gate to both inputs of a second NAND gate, then what you'll get is an AND gate, because as the NAND gate puts out a low, both inputs receive that low of the second NAND gate, and that will put out a high. And that's exactly how this works. Well, we're now nearly 40 minutes into this video, and there's no sign of a project coming out of it yet, and so we're going to rectify that immediately. And what we've got to do for this part of BTEC is we've got to design and build a circuit that's combinational logic and has 3 input variables. And so for this, we're going to do a module for an alarm system. Well, the first thing we're going to need then is a logic gate, and because I want 3 things all to be true before the logic gate puts an output out that's high, what I need is the equivalent of this, and that is a 3 input AND gate, and if A is true and B is true and C is true, then Q is true. And the Boolean expression underneath is Q equals ABC. So, from my stockpile of components, I can use either NAND gates, or transistors, or diodes. And considering diodes, they're a bit power hungry. And I've got a bit of an eye on the market, and looking at the portable properties of this device, I don't really want to be using diodes if I do want to turn it into a portable device. So that leaves me with the alternatives of NAND gates and transistors. And if we scroll down a bit, we can see how we're going to turn a NAND, or at least 4 NANDs, into an AND. I often find that the best way to work with these things is to work backwards. So let's switch everything off. As we know, if there is a low to a NAND gate, it will always output a high. Let me just get rid of Kaspersky there. It will always output a high. And if there is a high at both gates, it will output a low. So at the output gate here, what we need to do is we need to keep it constantly high, except on the occasions where A, B and C are equal to 1. To do that, we need to put a gate here that has a constantly high output, except on the occasions when A, B and C are equal to 1. And to do that, we need at least one of the inputs, or both, to be low. Now that's quite easy with input C because we can just strap it straight there. But it's not quite as easy with inputs A and B. So, what we have is if inputs A and B go high, the output here goes low, and the output here will go high, but we've still got low. If input C goes high, both outputs here will be high, both inputs here will be high, which makes the output here low. So, in all cases where the input is not fully equal to 1, then the output to this gate will be on low on one side or the other. There we are. Of course, if they are all high, we want to change. And we'll get a low and a high. There's a low there, great, so that'll now output a high. And that, of course, being strapped straight to input C will input a high, and the output will go low, and it'll be inverted to be a high output. Well, that's a bit of a convoluted solution. It will work, but it's very, very convoluted. And we do have an alternative. As an alternative then, we have this. And this is 3 transistors arranged for 3 inputs to an AND gate. And whenever 2 or 1 go high, the AND gate remains inactive. It's only when all 3 are high that the AND gate will switch on. And the pamphlets to go with this, I'll put the schematics for this AND gate and we'll see how we've done it. However, at the end, at the output, I've put a relay system. Now there's a reason for this, and the reason is that it's going to be difficult to fantail out. And what I might do is I might put something with a bigger impedance on the end of the AND gate, and that will disturb the balance and things won't work as they should. With a relay, I can use the AND gate to work the relay and keep the output from the relay separate from the input to it. And this has another consequence. This means that I can actually use 9 volts. And I want to use 9 volts because I've got an eye on the market. So what I can do is I can put a 9 volt siren in and make it a portable device as well as a static one, so it can work off batteries. Now, the logic gate is a 5 volt device and the siren can be 9 to 12. So, by using an electrically isolated system like this, I can accommodate those 2 voltages by putting in 9 volts and regulating down to 5. And if you watch the video on diodes, then you'll know I can do that with something like a Zener diode, or indeed I could use a standard chip regulator. So looking at the first of our input components then, we have a PIR sensor, and that's this thing here. And we look at it, you can see what it does. When it detects movement, the LED goes on. And what we've got is we've got a Fresnel lens, and underneath there is a pyroelectric sensor, and that consists of 2 strips of crystal carbonate, and when infrared light strikes those 2 strips, they cause a potential difference between the 2. And when the sensor's idle, there is no potential difference and it doesn't output a signal. But when it isn't, like now, and there is a potential difference, there we are, it will output a signal. And the length of time the signal's output for can be altered by this orange potentiometer here. So I'm going to leave it quite a short time, and if I put it back and let it settle down, what should happen is that as I put my hand in front of it and move away, the LED should go on. And that signal is what I'm hoping will work the input of the gate we've just seen. The next thing we need to look at is a reed switch, and this is it here. And it's mounted on a breakout board to make it easier to clamp down onto plastics or woods or whatever you're going to mount it to. But the reed switch is actually a form of contact switch, and what it is it's 2 strips. And normally they come together like that, but when you put them in the presence of a magnet, they'll come apart. Now I happen to have rather a large magnet there. So what I'm going to do is I'm going to move the reed switch closer to the magnet, move it away from the magnet, move it towards the magnet, move it away, move it towards, move it away and towards. And that's how the reed switch works. And you see these things on doors and windows, and they're all on security systems. So if an intruder opens a window or an intruder opens a door, then this can send a signal to the AND gate we're making to say, this is suspicious, have a look at this, will you? Our third component then is going to be a pressure mat, and a pressure mat is a rather large thing to get on a table, so we're going to do a little simulation on this breadboard here. So there are 4 buttons, and imagine these as an array of 32 placed into a mat. It doesn't matter where the intruder walks, sooner or later he's bound to put his foot on a button, or multiplicity thereof. It doesn't matter which one he does, it'll go off. So there we go, we've got a PIR sensor, we've got a reed switch, and we've got a pressure mat. Now let's see if we can hook them into the gate that we saw before, and see if we can make a working alarm system out of this. Well, before us we can see the completed project on a breadboard, and if I press any of these buttons now, which represent of course the pressure mat, absolutely nothing will happen. And that's because the door or the window or whatever is shut, as this reed switch is on the magnet. If we move the reed switch away from the magnet and wave our hand in front of the PIR sensor, and now just to prove it was the PIR sensor that was doing that, but the problem is that we've only got output for as long as anything's on high. If I shut the window again, no output. So here's what I want. To be an effective alarm system, this really needs to latch that relay, and there are 2 ways we can do that. We can do it mechanically and electrically with the relay, or we can put a thyristor in. And the easiest way is of course to put a thyristor in there. Now, despite what you might just have heard me say, putting a thyristor in here was not the easy option. In fact, it turned out to be a very horrible idea indeed. You might have heard me mention earlier the problems of fan out, and what I was finding was that as I put the thyristor here at the end of the gate, what we were getting was a problem with sending the signal to the gate of the thyristor and sending a signal from the thyristor to a transistor to drive the relay. So what I've actually ended up doing is latching the relay electrically by its own output. And if we look at that in action, there we are, and by doing that I can also put in a reset switch. Now normally a reset switch would be a key or perhaps a conceal button, and here it's just a normal push button. Now what happens here is that as the relay switches on, which it does by the output of the gate there, the normally closed switch will shut out and the normally open switch will become active. Through this blue wire, current goes up here and then it's shared. I have here a small signal diode which sends through this orange wire back to the signal wire of the relay, which is placed at the end of the gate there. It also comes down here through a 220 ohm resistor to connect with this LED, which is serving as a visual indicator for the output at the moment. It also comes back here to a switch which is connected directly to ground. And when I connect it directly to ground, the relay loses all of its inputs and switches off. Well, it certainly works. So the next thing I really need to do is I need to put that output to a transistor and see if we can drive a siren with it, working on 9 volts. After that, because it's looking a bit ungainly at the moment, what I'm going to try is doing the same with quad NANDs and see if that works any better. Well, what we have here then is the same circuit, however I've made a couple of changes. The first is this thing here, and now rather than making a power supply that can do 9 and 5 volts, what I've done is I've taken a commercially available one, which is a Red Wings power supply, and I've run a 9 volt power supply in, and we're getting 5 volts out at that end. Just to make sure, we'll have a quick look on the multimeter and see what's what. There we are, a shade over 5 volts. Here, coming from the same power supply, there's a crocodile clip. And what it's doing is it's going to this thing. Now this is a 12 volt siren, but it's really loud and really horrible at 12 volts. I bought them a few years ago as a job lot to make fire alarms with, and I defy anybody to sleep through these. So I'm running it at 9 volts because it's a little bit quieter at 9 volts, but it's still pretty horrible. And so when I do come setting it off, if you are wearing headphones, move them off your ears a bit because it will hurt otherwise. If we look, we should see, if we look, we should see here that we have a 9 volt supply. And there it is, not far short of 9 volts. So, let's shut the window, and it shouldn't work. Good. Let's open the window and waggle about in front of the PIR sensor and stand on the pressure mat. Ready? And as you can see, that is a pretty horrible noise. So there we go then. Let's break it into sections and see what we've got. We've got input number 1, the PIR sensor, and we'll shut the window so we don't set it off accidentally. Input number 2, the reed switch and magnet. Input number 3, the pressure mat, or the simulator thereof, which is actually 4 buttons. All going to a 3-input AND gate made out of these transistors. The 3-input AND gate is outputting to a relay, and whatever position the relay's in is outputting to this transistor, which switches the alarm on or off. So we made a 3-input AND gate with transistors there, and built a circuit around it to do something useful. Let's see if we can do the same with NAND gates, and then we'll go for a more modern version to finish off with. Well, what we're going to do next then is a NAND gate, and this is it, or rather 4 of them, all packaged up in this 14-pin chip here. This is a 74HC00M. And what you get in there is you get 4 NAND gates plus the power supply, positive there and the negative there. If you wire them up properly, like we saw in the drawing, then what you can do is you can turn these 4 NAND gates into an AND gate. And here's input A on this orange wire here, and here's input B on this red wire here, and here's input C on this blue wire here. And what will happen is, if I pull out input C, it goes low. If I pull out input B, it goes low. And if I pull out input A, it goes low. And it doesn't matter which ones you do, so there we are, A and B. B and C. A and C. It only goes high when all 3 inputs are high. Now, in theory, I shouldn't have any problems fantailing out here. And knowing how the relay worked, what we can do is dump it and replace it and put a transistor here and see what happens. So you can see the slight modifications I've made here. What I put in is a transistor. It's a 2N3904. It's exactly the same transistor as we've been using hitherto. And the collector here is attached to the 5-volt supply here. The emitter is attached to the LED, which in turn is attached through this 220 ohm resistor to the ground rail. The base of the transistor is being driven by the output from our NAND gate, and I've used a 2.2k resistor here to do that with, to make sure the base doesn't blow up. Well, let's plug things in. There's input C, there's input B, and there's input A, and the LED shines nicely. So it doesn't look as though we're going to have any problems with our fantail components coming out of this last gate, and the reason for that is that this last gate is acting both as a buffer and an inverter, and so it shouldn't alter the impedance on the rest of the circuit in the gates there. Well, that's the theory. So what we'll do now is we'll get the thyristor that we couldn't use last time, and we'll put it in and see what happens. So the new modifications then consist of this thing, CP106, plus some concomitant circuitry, and we'll just zoom out a little bit so we can see what that concomitant circuitry is. So the CP106 is a thyristor, and if you watch the video on transistors you'll know how the thyristor works and what it does. It turns the transistor here into a latching one. And what we've got is we've got the output here from our last NAND gate going through a 22k resistor to the gate of the thyristor. The anode of the thyristor here is put permanently into the 5-volt rail, and the cathode of the thyristor here is attached to a 220 ohm resistor, which in turn is attached to the base of the transistor. And this time I've collector loaded this LED, and I've sent the emitter to ground. Well, if we zoom out a little bit more, we can see what happens, and you can see that input A and input B are high. Input C, though, is dangling away in free space. You can see that? Dangling away in free space, being low. So let's put it high. And there we are. Now, if I take input C out again, and even input B, and input A, and I do what I like with them, wiggle them about as much as I want. It doesn't go off. And that's what the thyristor is doing. It's keeping the alarm, or the visual indicator of the alarm in the shape of the LED in this case, in a stable condition of being high, even though the gate may well have gone low or high. Now, I didn't bother putting a reset switch into this one, but it could be something simple as just turning the power off and turning it on again, and when one of the inputs is low it won't go on again, and when the inputs go high it will. So then, for our final breadboard proofing of the NAND system, so we're putting our original components back in place. We have the PIR sensor here, the door window lock here, and the pressure mat, or the simulator thereof, here, and of course the large horrible siren is making a reappearance. The large horrible siren is working off a 9-volt supply. It's being driven by an extra transistor I put in because I wanted to keep that LED there so that we could have sound and light to drive the 9-volt system. So let's shut the door or window or whatever, and nothing should work. Jolly good. Let's open the door or window or whatever and waggle our fingers about in front of the PIR sensor and stand on the pressure mat. Now this is going to get loud, so I'd remove the headphones from your ears. And there we are. And hopefully so let's remove the siren just in case we do set it off accidentally. Well, so that's feasible then, and you can see that we can learn some lessons from this. The first is that using this CMOS package here, the quad NAND gates, has made things much easier. I've had no problems fanning out my components here. Excuse me. And I'm not having any problems with my inputs. And the circuit looks cleaner and more elegant and just plain nicer. The second lesson is that the chip here is working on combinational logic. And combinational logic, we look at the inputs and that's all we care about. And the chip does the same. It looks at the inputs, that's all it cares about. If all three inputs are high, then the output is high too. If not, then the output will be low. By putting the thyristor in though, we've dabbled in some basics of sequential logic because now it latches, and of course by making a set and a reset for it, we've done some really very basic sequential logic there, and that's going to be the topic of the next video. So that looks to be a successful project on breadboard, and we could put it on some Vero board now and prototype it up, make it a working system. But what we're going to do is we're going to spend the next few minutes of this video looking at something a bit more modern, which does exactly the same job. And of course a modern variant on this is to use a microcontroller, and that's what we have here. This is a microcontroller, and the chip here is a programmable Atmel A28, and it sits in the board, and there's a power supply and a timer, and all the rest is really fluff. It's just breakout to make the chip easier to use. And we have our three components: the PIR sensor, the magnetic reed switch and the pressure mat simulator, and also of course the large horrible siren. And I'm going to shut the door or window or whatever. And hopefully nothing should happen. I'm going to open it. And the advantage in using this thing is that it cuts down on the amount of hardware we've got to use. It's slightly more expensive, but it does cut down on the amount of hardware. So we've got 1, 2, 3, 4 pull-down resistors for each input, excuse me, and a reset switch. And we've got a resistor for the LED and another one for a transistor, which is driving the siren from a 9-volt supply. The microcontroller itself is working on a 9-volt supply, but it has an on-board regulator just there, which will take it down to the 5-volt logic levels we need. The other thing is expandability. With the NAND gates and the transistors, we'd have to put a lot more discrete components in if we want to do anything with them. So, here we've got a lot more pins to play with to do inputs, and counting up from that I can actually do another 10, 11, 12 inputs, all without adding many more components in. Now we're going to look slightly at the code, because it does illustrate important things about and logic. And then we're going to look at some serial output that this thing is capable of doing whilst it's actually running, because it will round nicely off what we started with, which is Boolean logic. Well, what we're coding in is a dialect of the programming language C, and straight away, right off the bat, right at the top of the code there, you'll see that there is a Boolean variable, and a Boolean variable can be either true or false, and we'll see what that does in a moment. In the setup, we have setting up for pin modes, so 11 and 12 are output, and if we don't do that, we won't get enough current from the pins to drive the LED or the transistor. And serial begin 9600 means start serial communications with the IDE on the computer so that we can see what's going on. And 9600, of course, is the 9600 baud rate. Going down a bit. Now, if assert disable is equal to false, and the digital read is equal to A0, and the digital read of A0 is equal to high, and the digital read of A1 is equal to high, and the digital read of A2 is equal to high, then do all this. I'll just swing the camera around a little bit so we can see it. And basically we're switching on pin 11 and we're switching on pin 12. We only want that to do that when all of them are high, and using the code here we can treat those 3 pins as a 3-input AND gate. So let's have a look at the next line. A5 is a reset switch, although we don't really need it because we can reset the microcontroller by a switch on its own, or it does have a port which you can set a reset switch to. However, here I've done, if A5, the reset pin, is high, do the opposite. Switch everything off and make the Boolean variable assert disable true. If the Boolean if the Boolean variable assert disable is true, this can't happen, of course. So we've got a software input as well as our physical hardware inputs. And then as soon as A5 goes low again, we want assert disable to be false so that we can make this happen again. Now the rest of it down here just instructs the microcontroller to print out to a serial port so you can see on the computer exactly what it's doing. And we're going to have a look at that because it's important, and we'll see the zeros and ones that make up the Boolean logic system. And what we have here is a serial monitor that's monitoring what the inputs to the Arduino are and the outputs as well. Now, you'll see that there are 3 digits on the left hand side there, and what they're measuring is the inputs, and you'll see that the leftmost keeps changing. That's the PIR sensor, so every time I move in front of the PIR sensor it will change to 1. If I sit very still, hopefully it should change to 0 and stay at 0. Nope, I'm too much in front of the PIR sensor for that. So, if I undo the window catch, PIR sensor's gone off. Jolly good, let's put it back on again. There we are. So I've undone the window catch and I've got the PIR sensor at non-idle condition, and I've got 101. Again I've got 101. Now the 0 in the middle is the pressure mat. Now if I stand on the pressure mat and I set the PIR sensor off, there we are. Over here we're measuring the outputs, and I'm going to remove the siren so that we don't be disturbed by it while we're talking. So let's set the PIR sensor off, undo the window catch and stand on the pressure mat. And there we are. You'll see that the next column along goes to 1, 1, and that of course is the outputs of the Arduino. Now looking at some more output, you'll see that the inputs stay high regardless of what the output does. However, if I set the reset switch high, which is a 5, and you'll have to bear with me a moment, it's rather tricky to get to. There we are. You'll see that the Boolean variable assert disable has gone on to 1 and A5 is 1. If I set it back to low, assert disable goes to 0 and A5 is also 0 or low, and I've just set it wrong way again, just bear with me. There we are. So the lesson we could learn from this then is that there are in fact many ways to manage your logic. We've looked at something from the 1950s and we've gone right up to the 21st century. And of course it's all to do with price and expandability and whatever you want to do with it. So perhaps a transistor gate with 3 inputs is the best thing if you only want a system with 3 inputs. If you want a system with 3 inputs and a good reliable output that you don't need to mess about with, perhaps a NAND gate is the best idea. And of course, if you want to expand the system willy-nilly as and when the occasion requires, then really you're better off going with a microcontroller. And that's about it for combinational logic. So the next video we're going to look at is sequential logic.